looking back at a lot of different stuff that has to do with derivatives. So there's going to be a lot of rules that pop up. I would encourage you to at least save the handout that goes along with this video so you have it to reference, because there's a lot of rules written out on there that I'm not going to write out. I'm just going to refer to as they are shown up here. To begin with, limit definition of derivative. This is the first thing that we learn with derivatives, and it's combining our limits with the derivative concept, which is that the f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. That one can also be altered to be f prime of a number if the x is replaced with a number. The second rule that you see down there looks a little bit different, but kind of similar. Limit as x approaches a, so a is some number of f of x minus f of a all over x minus a. Now, we have actually seen some of these before as a limit problem that was difficult to do, and you might have had to do some work, especially that second type. And I'll show you what I'm talking about in a minute. Let's take a look at some examples using this, because a lot of times we're not actually having to do a big, long, drawn-out limit problem. If we can recognize, hey, this is limit definition of derivative, we can use our easy basic derivative rules to solve. So let's take a look at this first one here. We have limit as h approaches 0 of square root of x plus h minus square root of x all over h. Okay, so my first clue that this is a limit definition of derivative problem is the fact that it's as h approaches 0. Anytime you see that, you're pretty much guaranteed that it's going to be a limit definition of derivative problem. Now, notice that this one has the x's in there. So what this one is asking for is the derivative of a function. We have to figure out what function that is. Think about the rule that we just referenced. Okay, it said f of x plus h minus f of x. So the easiest thing to look at here is this portion. That can help you a lot. What was our original function? Take a look at this one. We're subtracting square root of x. That means that the original function, whoops, not f prime, but f of x, was square root of x, which is x to the 1/2 power. This is asking us for the derivative of that function. So all we have to do is find that derivative. Okay, remember general power rule? 1/2 x to the negative 1/2. If we rewrote that, that would be 1 over 2x to the 1/2, or 2 square roots of x. That's our answer. This is just asking us what's the derivative of square root of x. Now, take a look at the second equation over there. This limit starts out the same, limit as h approaches 0, and it looks very similar to the one we just did. The only difference is instead of an x, we have a 2. So on the one before, it was asking us for f prime of x. We just said the only difference is x is replaced with a 2 in this problem. So this one is asking us for f prime of 2. Well, we just solved for the derivative. The derivative is 1 over 2 square roots of x. So if we plug in 2, we have 1 over 2 square roots of 2. We can leave it like that. You can rationalize if you want to. If we went ahead and rationalize, let's see, we'd multiply by square root of 2 over 2, so we'd end up with square root of 2 over 4. Okay, so you can leave it either way, honestly. If it's a multiple choice problem, they're probably going to rationalize it. It really just depends. But we're less concerned with making it look pretty and more concerned with, can we understand what this question is asking us to do? Okay, last one there. This one, notice this one doesn't have an h. Okay, limit as x approaches 2 of 1 over x minus 1 over 2 all over x minus 2. Now, first of all, we notice that if we try to plug in 2, we're going to get 0 on the bottom, which we can't do. If we go back and take a look at this second limit form, f of x minus f of a all over x minus a. So let's take a look. F of x, okay, we're thinking f of x is 1 over x minus f of 2, because that's what x is approaching. Well, if f of x is 1 over x, then f of 2 would be 1 over 2, so that fits. And then it should be all over x minus 2, which it is. So here's what we have figured out. Our original function, f of x, is 1 over x. This is asking us for f prime of 2. So let's get the derivative. Remember, 1 over x is the same as x to the negative 1. So let's take that derivative. F prime of x would be negative x to the negative 2, which is negative 1 over x squared. Now if we plug in 2, because we want f prime of 2, we've got negative 1 over 2 squared, which is 4. So our final answer is negative 1/4. Okay. Hopefully we see now these are not usually about taking an actual limit. These are about recognizing limit definition of derivative forms and then just finding a derivative or finding a derivative and plugging in. They actually end up usually being pretty easy derivatives. Think about we were just taking derivative of x to the 1/2 or x to the negative 1 for those. Those were not difficult derivatives to take. It's actually understanding the concept of this is a limit definition of derivative, and I have to plug in sometimes a value depending on what it looks like. All right, let's take a look now at just some basic rules. I've written them out just to make sure we remember these. We already talked about, we just used the power rule with our examples before, but I've got it written out here for you again. Derivative of x to the nth power is n times x to the n minus 1. So power out front and then raise it to the 1 less power. Product rule. First times derivative of the second one plus the second one times derivative of the first. Quotient rule. A little bit more difficult. This is, again, don't necessarily memorize this as far as f of x and g of x. You want to think about the rule, because you're not going to have an f of x and a g of x necessarily. You may have different functions, or you may have just like an x squared plus 1 as your function. So memorize the process. Bottom times derivative of top minus top times derivative of bottom all over the bottom squared. Okay. We are going to work through some examples using these, but before we do that, we're also going to review some other formulas. These are probably a little bit more difficult and hard for us to remember. So I wanted to make sure to take some time to look at them. Our trig rules. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of cosecant is negative cosecant cotangent. Derivative of secant is secant tangent. And derivative of cotangent is negative cosecant squared. These are just ones we have to have memorized. The more and more we use them, the more and more you have them memorized. And last little rule there that I want to make sure to remind you of, well, it's not little because it ends up being very important, is chain rule. Now I have two different formulas there. The first one is what's called more the formal definition of chain rule. This is more the formal one. We use this a lot when we have a table of values. Okay, so this ends up getting used mainly when we have a table of values. The next one is the more generalized version that makes it a little bit easier to see what we're doing as we're working through something. This is kind of like the power rule for chain rule. So it starts the same, but notice instead of x to the nth power, we now have u to the nth, where u is some function of x. So n times u to the n minus 1, that looks normal. The extra piece is that we have to multiply by u prime. Okay, think about general power rule. It's the same, except think about if you multiply by u prime, your u would be x, and the derivative of x is just 1. So it's the same thing. It's just generalized for when you have a plain x. All right, let's jump in with some examples. First of all, find the derivative. So we're just going to take the derivative here. We're not going to do anything with it yet. We're just taking the derivative. For number 1, we could go ahead and FOIL this out and then take the derivative, but what I'm actually going to do is I want to practice product rules, so I'm going to do that with problem number 1. So product rule says first times derivative of the second one plus second. We want to multiply now the second one times the derivative of the first, which would be 8x. Derivative of 4x squared would be 8x. So if we do that, try not to run out of room, 4x squared times 4x is going to give us 16x cubed. 4x squared times negative 5 is negative 20x squared. 3 times 4x is 12x. 3 times negative 5 is negative 15. We're going to keep going. 2x squared times 8x gives us 16x cubed. And negative 5x times 8x is negative 40x squared. Okay, if we finish up here, combining like terms, 16x cubed plus 16x cubed gives us 32x cubed. Negative 20x squared and negative 40x squared is negative 60x squared plus 12x minus 15, and that would be final answer here. All right, I'll change colors for the next one. For the next one, we're going to have to use a quotient rule. So let's get started here. Bottom times the derivative of the top. Derivative of 3x squared is 6x minus the top times the derivative of the bottom. Derivative of 4x plus 5 is just going to be 4. All over the bottom squared. Okay. Let's try to simplify down. I'm going to take a look at what this would be up here. 4x times 6x gives us 24x squared. 5 times 6x gives us 30x. 4 times 3x squared, we're going to subtract 12x squared. And then negative 1 times 4 is a negative 4, but we have a minus out front of that, so we're going to be adding 4. So let's combine 24x squared minus 12x squared leaves 12x squared plus 30x plus 4 all over 4x plus 5 squared. And we don't need to simplify down. We can just leave this one as that quotient. We don't need to try to simplify unless we thought something would cancel, but obviously 4x plus 5 is not going to be a factor of the top, so we don't have to worry about trying to cancel or simplify down. And again, remember it also, whatever you're trying to do with the problem, in this case we said find the derivative and simplify, so that's what we want to do. Say we were doing a problem where we were trying to find the equation of a tangent line, we wouldn't have to simplify all the way down. We could use that original equation once we took the derivative without simplifying and plug in there depending on what we needed for the problem. All right, here's a couple more. We want to find derivative, so let's keep working here. Number 3. Y prime, the derivative, we're going to have to use chain rule here. And everything that's in our parentheses would be our u. So remember our rule, general power rule for chain rule. 4 comes out front. Now times all of this to the third power, we reduce by 1, times the derivative of what's inside. Derivative of 2x squared minus 3x is 4x minus 3. Okay, so we can actually just leave it like that. We can't really do anything else, can't simplify down anymore. We could take an x out of this term, but we're not going to do that. That would be going a little bit too far, more than we would need. Number 4. Now, this is a nice one because we're going to practice everything. We're going to put it all together because take a look. We've got a product rule. We have 2 things multiplied. We also, within that product rule, when we take the derivative of the first term, we're going to be using chain rule. So let's take a look at this one. All right, first times the derivative of the second. Derivative of 4x squared plus 9 is 8x plus the second one times derivative of the first. So chain rule, 2 times 3x minus 1 now to the first times derivative of what's inside, which would be 3. Let's talk about simplifying this one down. Things they have in common that we could factor out of each one. We have an 8x, we have a 2, so we could take out a 2. And they both have at least one 3x minus 1. So let's see what would be left. If we look at this first term here, divide out a 2, and we're going to be left with 4x. And then we still have 3x minus 1 once we factor 1 out. Let's look at the second term. We're going to take out a 2, which we already did, and a 3x minus 1. That leaves 3 times 4x squared plus 9. Okay, so we just need to simplify down a little bit. Inside here, we've got 12x squared when we distribute minus 4x plus 12x squared plus 27 when we distribute that 3. Okay, let's simplify down. Combine our like terms. 12x squared plus 12x squared gives us 24x squared minus 4x plus 27. Okay, and now that would be simplifying down beyond that first step. If we were finding, say, again, a tangent line and all we needed was the slope at a specific value, we could have substituted in here at this first step. Okay, we would not have had to simplify down anymore. It really depends on what the question is asking of you. All right, let's try some trig. Number 5 here, we have sine of x, sine squared of x, which we can think of as sine of x all squared. That might help a little bit when we're trying to take derivative because we have to use chain rule. Power out front. Sine of x is now to the first power, and derivative of sine of x is cosine of x. So this one is just 2 sine of x cosine of x. Now, this is a free response style question, then you can leave your answer like this. If this is multiple choice, I guarantee you they are going to go ahead and rewrite this as sine of 2x. Okay, that's a double angle identity that we learned. I just wanted to remind you of it. That gets used a lot. The sine double angle formula gets used a lot. The other ones don't really get used as much to simplify down, but definitely sine double angle gets used a lot. All right, let's look at this next one. We're going to kind of do like we did before. We're going to put some stuff together. We've got a product rule, and then with the cosine squared, we have a chain rule. So let's talk about taking this derivative. Using our product rule first, times derivative of second, so times cosine, plus the second one, times the derivative of the first one. Now, derivative of cosine squared, remember that's like, whoops, cosine of x all squared. So we got to use chain rule. So times 2 times cosine of x now to the first times derivative of what's inside, which would be negative sine of x. So let's just tidy this up a little bit. Cosine squared times cosine gives us cosine cubed of x. And then we are going to have a negative that we're multiplying by, so we're going to subtract. And we have 2 cosine of x sine squared of x. And we can just leave it like that. We could take out a cosine, but that's really not going to help us because then we'd have cosine squared minus 2 sine squared. It's really not going to help us simplify down at all, so we just leave it like this. Okay, now let's take a look at actually using these for something. 7, we're going to find the equation of the line tangent to the fourth root of x at x equals 1. So let's think about when we have a tangent line, we need the x-coordinate, the y-coordinate, and the slope. Okay, for all of these, they've already given us the x-coordinate, so that's taken care of. We still need the y-coordinate and we need the slope. Y-coordinate's easy to find. We just plug the x into the original function and get the y-coordinate. The slope is a little bit harder because we have to take the derivative and then plug in the x value. So let's take a look at this first one. Y is the fourth root of x, which we can rewrite as x to the 1/4. So when we take that derivative, we have 1/4 x to the negative 3/4 when we subtract, okay, which is the equivalent to 1/4 times x to the 3/4, just to make that a positive exponent. Okay, now we already have our x-coordinate, like we said, it's x equals 1. Let's talk about finding y-coordinate. We plug 1 into the original function. The fourth root of 1 is 1. Let's plug into the derivative to get our slope. 1/4 times 1 to the 3/4 is just 1/4. So if we write the equation of our tangent line, we'd have y minus 1, the y-coordinate, equals m, the slope, which is 1/4, times x minus the x-coordinate, which is 1. Remember, a lot of times we use point slope form because it's easy to plug it in and we don't have to simplify down. If it's a multiple choice question, they may reword or rework around and have it in slope intercept form, or maybe that standard form ax plus by equals c. That could happen as well, but this is where we start from. All right, let's take a look at number 8. We need the same things. We already have the x-coordinate, x equals 1. we need y coordinate, and we need the slope. So let's go ahead and find that derivative. Let's use quotient rule. Bottom times derivative of top minus top times derivative of bottom all over bottom squared. Okay, let's think about what we'd have. This would become 2x squared plus 2. And over here, we're going to subtract 4x squared. So we'll have 2 minus 2x squared. And on the bottom, whoops, I forgot my squared earlier. X squared plus 1 all squared. So let's try to find our different values. We need f of 1 to get the y coordinate. If we plug that in, we have 2 times 1, which is 2, over 1 squared plus 1, which is 2. 2 over 2 is 1. Now let's find the slope. If we plug in 1, we have 2 minus 2, which is 0, over 2 squared. So 0 over anything, as long as it's not 0, is still 0. Now, that means our slope is 0, which means we have a horizontal tangent. Horizontal lines, remember, are y equals. So our tangent here is just y equals our y coordinate, which we found to be 1. All right, let's try the last one. We want to find this tangent line, so we've got to do some trig here. Let's find the derivative using product rule. First times derivative of the second one plus the second one times derivative of the first. So I'll just put that 2 out front. Let's plug in pi over 2. So 2 times pi over 2 times cosine of pi over 2 plus 2 times sine of pi over 2. Well, cosine of pi over 2 is 0, so this piece is gone. Sine of pi over 2 is 1, so 2 times 1 is 2. That's our slope. We need our original y coordinate, so g of pi over 2 would be 2 times pi over 2 times sine of pi over 2. 2 times pi over 2 becomes pi. Sine of pi over 2 is 1. Pi times 1 is pi. So now let's write that equation. Y minus the y coordinate, which is pi, equals our slope m, which we said was 2, times x minus the x coordinate, which is pi over 2. And of course, we could simplify down if we needed to for the problem, but for this, we're just going to leave it as it is. All right, one more question that I want to go over. Find the equation of the normal line to the given function at the given value. Okay, so we've done tangent lines. Big thing to remember, I'm not sure if we talked about this before or not, but in case we haven't, let's talk about it. Normal line is perpendicular to the tangent line. Okay, so that means we're going to do this problem just like we did before with one extra step. Whatever we get for the slope, we're going to flip it and change the sign, okay? Because perpendicular slopes are negative reciprocals of each other. So let's get started. Remember the things that we need. We need our x-coordinate, y-coordinate, and slope. We have our x-coordinate. We could go ahead and find our y-coordinate if we wanted to. Let's plug in 1 plus 2 times 2. 1 plus 4 gives us 5. On the bottom, 3 minus 4 times 2, so 3 minus 8 gives us negative 5, which gives us negative 1 for the y-coordinate. We need the slope, which means we're going to have to find the derivative. So we're going to have to use quotient rule, bottom times derivative of the top minus top times derivative of the bottom all over bottom squared. And remember, we don't have to simplify down if we don't want to. We could go ahead and plug in. Let's say we go ahead and plug in the 2. 3 minus 4 times 2 is 3 minus 8, negative 5 times 2 minus 1 plus 2 times 2. 1 plus 4 is 5 times negative 4 all over. I keep forgetting that squared. 3 minus 4 times 2, so 3 minus 8, so negative 5 squared. That's going to give us negative 10 plus 20 all over 25, which is 10 over 25, which is what? 2 over 5 for our slope. Now, here's what we have to remember. Normal line is perpendicular, so we need to flip it and change the sign. So our slope is going to be negative 5 over 2. Okay, so let's write that line. I'm running out of room here, so I am going to do some erasing. Let's see if I can do that. Okay, let's just do a little bit of erasing, and then we're going to write out that equation of that line. We need all three things, x-coordinate, y-coordinate, and our new slope. Remember, again, the reason that we flip that and change the sign is because the normal line is perpendicular to the tangent line. So, equation of our line, y, that does not look like a y. Yeah, here we go. Y minus the y-coordinate, but it's a -1, so we have y plus 1 equals our slope, which is -5/2, times x minus the x-coordinate, which is 2. And that would be our equation of the line normal to this function at x equals 2. Hey guys, you're going to have a lot of practice, a lot of time to go back through these derivative rules and make sure we still feel comfortable with these and working with these to find different things. We'll take a look at some applications, especially with tangent lines, in the next few days.